in a gas, the molecules are all moving around really fast, so they're kind of bouncing everywhere and they're really spread out. And then when you get a little bit colder, that means that their energy drops, so they're moving more slowly. Like when you freeze something, it becomes a solid, and they just kind of calm down even more. And then this is kind of cool because you can see it bubbling up and everything. That's basically the liquid nitrogen is boiling because you're adding heat to the system from the racquetball.
The reason it does that is because the kinetic energy of that one is
a piece of one that we smashed earlier, and basically once it warms up, it returns back to the kind of spongy state that it was before. One of the cool things about liquid nitrogen is that as it cools down to just normal air, you can see the balloon just kind of like crumble in as the gas rises, and then as soon as it heats up, it expands back out just like that.
If I let it go,
sometimes the gas compresses enough that you can see it as a liquid in the bottom. It's kind of hard to see. Yeah. So it's enough to turn the air inside into a liquid.
There we go.
Do what? Oh. Okay.
It's really neat because if you drink water,
oh, really?
crazy hair.
But yeah, this just kind of turns back.
One of the other effects is the directionality here.
Yeah.
Now, one of the interesting things is because of the way that the energy adds up. If I say move 2, do you think it'll just hit off 1 with twice as much energy? Will it move the other 3 with just a little bit, or what? Actually, a really good attitude. Honestly, like, that is pretty much how scientists end up treating unknown problems. Is you really don't know what's gonna happen.
But yeah, and then like
Go and test it and see what happens, and then try and figure out why that happened.
yeah.
So one of the harder ones to figure out. Like, you'll notice, it was just 2 moves, right? And if I do 3, you'll notice that once again,
One of the other things you can do
3 moves.
we have
One of the harder ones to get your head around
we push
is this one.
or we poke holes like one in each side of the
So,
ball. And so when you did
this is a little bit harder to visualize before. So it's actually just gonna leave this one still afterwards.
And then when you bring it out into the normal air,
And that one actually looks pretty
makes
nice.
it, or, yeah, liquid nitrogen. Yeah, I thought that this one would probably cool this
Pretty fast.
and have it magnetic like that. And so
Like, honestly, the longer I hold it, the faster it goes. And like, the point is mostly that it goes really fast. And the faster it goes, the harder it gets to do this.
basically the magnet.
Like, this is the same sort of thing that makes it difficult to
It kind of freezes the field.
tilt your bike over.
So then it can act like
If it's going really fast, it's hard to fall off because it wants to stay spinning in the same direction. My right hand, if I let my right hand go, this end will just fall. Gravity is pulling down on that. It wants to fall, right? But that would mean it's spinning in a different direction. There will be force opposing it. So what actually happens is that it spins in a slightly different direction, but not as different as this, which is really hard for gravity to do. The faster it's spinning, the closer to the horizontal it will stay when I let it go like that. It is a really fun effect. If I form a system of me, the spinning wheel, and not spinning platform, what will happen if I change the momentum of the wheel, it'll gain momentum
that's part of why it's
platform.
well, some people
As
will
long
like
as
splash
I'm
into
taking
the
the momentum from the
stuff, and you can usually get away with it because
And
the
you
back
notice
is so
that
fast. But it's really
depending
bad
on
to, like,
which direction I'm turning the wheel,
because it stays inside and then it
direction.
expands and
because I'm giving it a different direction of angular momentum. Angular momentum has a specific direction related to the direction the spinning object is spinning in.
So what happens when I rub the balloon against my hair is that this neutral balloon is going to strip off some electrons from my hair, but my hair still retains that positive charge. So positive and negative is going to attract. So I can make my hair stick up. It's kind of exactly like magnets. When you have a positive and negative magnet, it's going to stick together. If you have positive and positive, it's going to repel. If you have negative and negative, it's going to repel. The same thing happens with electricity with positive and negative charges. So I'm going to use a device which is basically the epitome of static electricity. Has anybody seen one of these?
We have a racquetball, and so racquetballs are normally
Okay. Does anybody know what it's called?
You can squeeze them easily, and so there's kind of space.
It's not a pop quiz or anything, but this is a Van de Graaff generator, invented in the 1800s by some guy with the last name Van de Graaff, and it works on principles of static electricity. So what we have in here is like a silk belt that when I turn the crank, the silk belt is just going to rotate. Inside of this metal ball, we have a little comb that is right up next to the silk belt. The silk belt is going to be transferring some of the negative charge to the comb, and the comb is connected to this metal ball, and metal is a good conductor. It will hold on to whatever charge that you give it. So we're going to give negative charge to this ball, but the other side of the belt is going to take all the positive charge and deposit it on this wand. And when I move the wand close enough, we're going to be able to complete the circuit and create a little spark coming off. Has anybody opened a package and all the packing peanuts came off and stuck to their own or something? We've all had it happen to us. What do you think is going to happen when I start to turn the crank? It's gonna, yeah, it's just going to explode. Why would that happen? What kind of a charge would I be building up on these packing peanuts?
And so if you guys remember,
Are you sure?
pressure and volume.
Negative charge. It would be the same charge that we're building up, and the same charges are all going to repel each other, and this is going to just explode. So rain shower and packing peanuts. We talked about all sorts of types of waves. Light coming from just these lights in this room are emitting light in a very narrow band of the electromagnetic spectrum called the optical band of light. So we have red through blue wavelengths of light that our eyes can actually detect. But in the universe, there's much more than just this little narrow band of wavelengths of light. So telescopes, back in the early days with Galileo, they kind of had glasses, and then some Dutch person used a series of lenses to go look off into the sea, and Galileo kind of stole the idea of using lenses to maybe look at the stars, see what's up there. So Galileo came up with a series of lenses, and you can use a series of lenses to focus light to a point. And we have all sorts of types of lenses here, including these, let's see, concave lenses that I can use to focus light to a point. So can everybody see here that I have a kind of, this is what we call a concave lens with two kind of, two sides that are kind of going outward, protruding outward. And when I put this on the table, if anybody wants to get a little bit closer, feel free to, but I'm able to focus light to a point with a concave lens. So can everybody see the little point on the table that this is focusing to? And what telescopes are a series of lenses that that we can use to focus light. But the other thing that we use in astronomy are mirrors. Maybe in the 1700s, they decided that it's really hard to make really big lenses, and the bigger the lenses that you have, the more light that you can gather from like the stars. And it was getting really hard to build really big lenses. So Isaac Newton decided, hey, mirrors do kind of the same thing as lenses. What we want to do is focus the light to a point. So what I have here is both a concave mirror and a convex mirror. So this is going to act kind of like the lens, but instead of having the light rays focus over here, we're going to focus to a point over here. So it's kind of the same concept. But there's another type of lens called a convex lens, where instead of having kind of two sides going like this, they're both kind of diverging. And we can make that, make the light rays kind of go outward instead of inward. And there's all sorts of cool lenses that you can make to make light do whatever you want. But most of the time, we want to focus light to a point. So we use concave mirrors that can focus light to a point inside. If you use the other side of the mirror, it's going to try to diverge all the light to the outside. It's kind of neat. Its light is polarized, but when I put them together, if I rotate them, you're going to see less and less light coming through. And that means that the polarizers are at 90 degrees to each other when the minimum amount of light is coming through. So if I twist them back around, you're going to see it clearing up a little bit. So polarizers are pretty cool.